Hi everybody, this is Professor Mankowski, and in this video we're going to go ahead and we're going to go through section 7-2. So where we'll begin is a recap of section 7-1. In section 7-1 we found out that if somebody wants to estimate a population average, a pretty good thing to do is to start by taking a sample out of that population. And then from the sample, we're able to calculate our sample average. We can report our sample size. We can report our confidence level and the population standard deviation. Now, of all these numbers, it's going to turn out that one of them is a little bit unrealistic to know, or rather to assume that we're going to have it. And which is the culprit? It turns out that it's going to be the population standard deviation. The reason why is because most of the time we're not going to know anything about the population standard deviation, so it doesn't make that much sense to keep assuming we're going to be able to use it in the formula. That means if we didn't know the population standard deviation, what could we still do to calculate an interval without knowing it? And that's going to bring us straight into section 7-2. 7-2 is how to calculate the population average when we don't know sigma. That being said, then how can we do the job? How can we still calculate the interval if we're missing a number? And the answer is we're going to have to use something as an estimate for sigma inside the formula. Well, what then do we use? The best estimate that we can use for sigma is going to be the sample standard deviation S. So does that mean it's okay to go into the formula and just switch sigma with an S and just kind of keep our mouth shut, not tell anybody what we did? Like, is that an okay thing to do? Is that good? And the answer is that's good, and that's also bad. There's some good things that happen and some bad things that happen when we do that. The bad news is that if we're going to go ahead and do this and we have a really small sample size, that means the number we end up calculating for S is going to be very unreliable because it's based on just a little bit of information. Consequently, when we calculate the interval, that means we have a really risky prediction for mu. And we have to do something about that. So what's the fix? The fix is that we have to take our interval and we have to put a lot of correction factor in it, meaning we have to do extra cushioning and make that interval unusually large to compensate for the fact that we don't know anything about the sample standard deviation. The flip side of this is also true. If the sample size increases, that means the number we're using for S is more reliable because it's based on much better information. And the challenge that comes up is we don't need this unusually large interval with all this extra cushioning anymore. We can make it much more narrow. How do you know how much cushioning to put in, how much to take out, when to put it in, and when to take it out? Like, how do you adjust for all that? And the answer is we're going to end up switching from the Z distribution to something called the T distribution. The T distribution is going to take all this extra adjustment factor, this extra cushioning, it's going to put us on autopilot. So when we do the formula, all this extra interval correction is going to be taken care of automatically for us. Now, before we get into formulas, the first thing we're going to do is we're going to take a look at how the T and the Z distribution are similar and different from each other. So on this screen here, we have a Z curve superimposed over a T curve. And there are some similarities. Both the curves are bell-shaped. They're both symmetric about the mean. The mean, the median, and the mode are going to be located at the center, and neither curve will touch the x-axis. So how about differences? The two biggest differences are that the T curve is actually going to be a family of different curves, and the T curve is also wider than the Z curve. The reason why it's wider has to do with the correction factor that's going to get added into the formula for us. So speaking of formulas, let's take a look at the Z formula and the T formula, and let's compare them to each other. If we bring up on the screen the Z formula, we'll find out that the T formula is quite similar to it. The T formula is going to, instead of a Z, have a T, and instead of a sigma, the T formula is going to have an S. Now, the most important thing that you need to remember about the formulas When are we supposed to use the t-distribution formula? Only when the population standard deviation sigma is unknown. Okay, having said all that, how do we read the t-tables? We're going to need two ingredients to read the t-tables. And the first thing that we're going to need is the sample size. And when we calculate the sample size, we're going to have to calculate something special called the degrees of freedom. And the degrees of freedom we're going to get just by taking the sample size and subtracting 1 from it. The second thing that we're going to need is the confidence level. Let's go ahead, let's take a look at the t-tables and let's practice them out. So we're going to take a couple cases of just finding out the t-tables, rather our t-value based on a sample size and a confidence level. And then once we've got that down, we'll move to some full-blown practice exercises. So first thing that we have is sample size of 30 and 95% confidence. What I'm going to do is right away, I'm going to write down that I have 29 degrees of freedom because I don't want to forget to calculate that. Second thing I'm going to do is I'm going to look into my t-table, table F, and I'm going to go to the leftmost column where it reads degrees of freedom. If I go all the way down that column, I'm going to find the row for 29, and I'm going to underline that row for 29. I'm going to then bring my confidence level into the picture. I've got 95% confidence, so I'm going to go into that top row where it says confidence level, and I'm going to find the column corresponding to 95% confidence. I'm going to find out where the column intercepts the row, and I'm going to write down that value, 2.045. Now, notice all the values in the t-tables are positive. That's because the inventor of the t-table knew that the distribution was symmetrical, so they only wrote down the positive values. Mentally, we have to remember that there's a plus minus involved in it. Let's do one more case of reading the t-tables. We're going to use a sample size of 10 and 90% confidence. So right away, first thing I'm going to do is write down that I have 19 degrees of freedom. I'm going to go into that same column. I'm going to identify the row for 19 degrees of freedom, and I'm going to underline it. Next, I'm going to go and I'm going to pay attention to my confidence level. I'm going to go into the row for confidence intervals. I'm going to find the column corresponding to 90% confidence, and I'm going to find out what's the intercept of the row in the column. And it looks like that's 1.729. So I'm going to make a note of that. Now that we know how to read the t-tables, let's go ahead. Let's take on some practice exercises. Pause the video for just a minute, read through the practice exercise. Okay, so first thing I'm going to do is I'm going to write down all the numbers I've got from that question. Now I'm going to go back into the question and I'm going to start to see how I can identify the numbers. First thing they did was tell me a sample of 6 college wrestlers. The way that they're saying to me, the sample consisted of 6 college wrestlers, that lets me know that 6 is my sample size. And noticing right away, I'm going to put in my degrees of freedom. The next number was 276. And 276 is the average weight. So at this point, it could be X bar, it could be mu. If I notice it's connected into the sample size of 6, that lets me know 276 is going to be my X bar. They also told me that my sample standard deviation was 12. That means that S belongs to 12. And I'm making a big deal out of that S. Why? Because now I know not to use the Z formula anymore and to use the T formula. They also mentioned the number 310. But that 310 doesn't appear to be connected to either the sample size or the population. That means I'm probably going to end up using it for later. 90% confidence we need to obtain from our tables, and the value for that comes out to be 2.015. We've got everything we need now to roll out our formula, so I'm going to bring that up on the screen here, and I need to move some things out of the way. Okay, I'm going to go back into play mode. Okay, that's better. WebEx controls were covering up some of the things I needed to read. So I have my formula, x bar plus or minus T alpha over 2 times S over the square root of n. I'm going to work on my left side first, and I have 276. Left side will go with the negative, and the right side, 2.015 times 12 divided by the square root of 6. That's going to calculate out to 266. The only difference between the low side and the high side is going to be the plus and the minus. When I put in the numbers on the right side, I end up with 286. Okay, so it looks as if we have this other question down here, because the coach is claiming that there's a wrestler that weighs 310 pounds. Would that claim be believable? Well, let's start to consider everything that we know. First of all, we're 90% confident that the true weight of the wrestlers is in between 266 and 286 pounds. That means that when we look at their number, 310, that's way far out of the maximum threshold, 286. And being that we're 90% confident that the population average is in between 266 and 286, there's a very small percentage chance that the real population average is outside that interval. That probably means we don't really believe what the coach is saying. Let's go ahead and take a look at one more practice exercise. And take a minute, pause the video if you need to, and with that video paused, see if you can figure out some of the symbols. Okay, so I'm going to go ahead, I'm going to write down everything from that question, all the numbers they gave me, and let's start to identify things. They've written in 13 thunderstorms. The meteorologist sampled 13 thunderstorms. So I've got a quantity of 13 of something. That's going to be my n. So I'm going to go straight away to 12 degrees of freedom. 15, rather not 15, the average speed. Well, they did say the average speed within the context of 15. My 15, it could be a mu or it could be an x bar, but it's connected to my sample size. So that means that my 15 is going to end up being x bar. Now, the last piece they gave me, well, not the last piece, but the next piece was the sample standard deviation was 1.7. Since I know 1.7 goes to the sample standard deviation, that tells me 1.7 is S, and again, it lets me know that I'm going to be using the t-distribution. 99% confident is going to correspond with the value of 3.055 off of our table, and now we have everything that we need to run our formula. Pause the video for just a few minutes and see if you can go ahead and calculate out our low side and our high side. All right, let's find out what the low side came out to be. Low side is going to be 13, and the high side is going to be 16. Okay, so we could say that we're 99% confident that the average speed a thunderstorm is going to travel across the area is going to be between 13 and 16 miles an hour. And they also kind of asked a part B question. They said if the meteorologist wanted to use the highest speed to figure out, if meteorologists wanted to use the highest speed to predict the times it would take storms to travel across the state in order to issue warnings, what figure would she use? And the answer is they're probably going to go with the 16 miles an hour figure. Why would they do that? Why would they use 16? Well, the reason is they probably want to give people the maximum amount of preparation.